Hello, my name is Noah Hai, and this is Physics 2211, Lab 5, Slinky Drop. The purpose of this lab is to analyze the motion of a slinky as it is released from rest, understand how tension, gravity, and drag contribute to the movement, determine if the bottom of the slinky stays stationary, and lastly, use tracker and closed grip to compare them. For fundamental principles, we've got Newton's second law, which is F net equals dp over dt. And for this lab particularly, F net equals tension force plus gravity plus drag force. Here, tension force will exist until the top end of the slinky hits the bottom end. Theoretically, tension force would not exist once a person drops slinky. However, in this case, the information of the tension force gets delivered once the top end contacts with the bottom end. And as always, we need update formulas, like velocity update formula and position update formula, to find in the change of velocity and position. So here is a brief preview of the result. The experimental and computational models were slightly different but showed similar trend. Okay, so for tracker, the object mass was 0.25 kilograms. Initial position was, we only care about y axis, so it was 0.5 meters, and initial velocity was 0 because it was released from rest, and time elapsed was 8.88 seconds. For the computational model, same thing. The ball mass was 0.25 kilograms. Ball position was 0.5 meters on the y-axis. Ball velocity was 0 since it was released from rest. Time started from 0. Gravity, obviously 9.8. And then we used unit vector. And since we only deal with y-axis, we only have a value for y. Other than that, it's 0. And then drag force is just 46. I just randomly figured out to match the experimental model. So for the actual coding, it was divided into two parts because until t equals 6.32, the object doesn't move. I mean, the bottom end of the slinky doesn't move because the tension force and gravity cancels out each other. So in order to model that, it was divided into two parts. So the first part looks like this. We have tension force and the gravity force canceling out. So basically F net equals 0. And then we use Newton's second law and the update formulas to, figure out its position over time. And for the second part of coding, we have our t between 6.32 and 8.88, and then we've got our gravitational force and drag force, and then drag force, its role is to lower down the gravitational acceleration. And same thing, we've got our velocity and position update formula, and then also update our t. And that's it for our computational model, basically. So as a result, the bottom of the slinky stayed stationary until t equals 6.36 seconds because tension force and gravitational force canceled out each other. Although there is no real tension force, it takes time for the bottom of slinky to get the information that there is no longer tension force acting upon. And after t equals 6.36 seconds, the slinky started accelerating downwards due to gravity, and we can think of this as the time elapsed until the top end of the slinky makes contact with the bottom end. There are some possible sources of errors, such as calibration error when using tracker, low precision in locating the position of the mass in tracker, and imprecise measurement of height, weight, drag constant, and so forth. So in conclusion, since we didn't exclude drag force this time, the experimental model and the computational model showed similar movement along the y-axis. And as expected, the bottom end of the Slinky did stay stationary until it contacted with the top end. Okay, that was our final lab report, and thank you for listening.